Welcome children. Now we are going to discuss about the heating effect of electric currents. See, in the last class we discussed about the heating effect of electric currents. Today we are going to discuss about what are the applications of heating effect of electric currents. Before that, what are the things we discussed in our previous class? When electric current passes through any appliance, a certain amount of heat is developed. And in some appliance, we make use of it. In some appliance, some of the appliances such as electric iron, electric heater, etc., where we use or where we make use of heating effect of electric current. When electric current passes through a resistor, the heat developed can be calculated or obtained by using Joule's law of heating. From that we got the relation H is equal to VIT and also H is equal to I square RT. H is equal to VIT and H is also equal to what is I square RT. Now see, with these relations, that means here H, the amount of heat producing due to the passage of electric current, V, the potential difference that maintains the flow of current, and I is the rate of flowing of current, and T is the time that is taken in second. Now see, here this current can measure by using ammeter by the relation I is equal to V by R. R is the resistance. Now with these relations, we want to solve two problems which is here given. First of all, before we are going to discuss about applications of heating effect of electric current, we can solve that problems at first. See, here the question given. First one is an electric iron consumes energy at the rate of 840 watts. That means electric energy that it consumes is 840 watt. When heating is at the maximum rate and 360 watt when the heating is at the minimum, the voltage is 220 volt. See, an electric iron consumes energy at the rate of 840 watt when heating is at the maximum rate and 360 when the heating is at the minimum. The voltage is 220. What is the current and the resistance in each case? That means we want to find out the current and resistance in each case. See, maximum is 840 watt and minimum 360 watt. First of all, we want to find out current and resistance when the power is maximum. That means 840 watt. We know P is equal to VI. That means voltage into current. From this we can find out current I is equal to how we rewrite this equation to get I? Can you say? P is equal to Vi or I is equal to P by V. I is equal to P by V. See, this I is equal to P, that means 840 by and V 220. On 0 we can cancel from up and down. Again we can divide this with 2. Here 11 times. Here 4, 2. Now 42 we want to divide with 11. 42, 11. How many times? That is 3 times 33. 11. See, here I is equal to P by V, or that is 840 by 220. All times here 1 on 0 we cancel. Then in 22, 11 times 2, here 42. 4 and 2, 42. Now see, here 11 times 3, 33. Now we can take out from this how much this will come. That means from 42. Here only is taking on 9 decimal 0. In 90, 8 times 88. That means 2 and 0, 1. That means how much will be its value? Its value is we got how much it is 3.81 ampere. Its value is 3.81 ampere is the current it drawn when the power consumed is maximum. Then we want to find its resistance. So next we want to find out the resistance. We know R is equal to V by I. R equal to V by I. That means V, how much? That is equal to 220 by I. That is 3.81. That means 220 divided by 3.81. It is equal to, by removing 2 decimal, 220, putting 2 more 0, we get 381. 22, that means 22,000 divided by 381. See, when we divide this, we get that is 57.60 ohm. When we divide this value, that means 220, that means 22,000 divided by 380, we get its value as 57.60 ohm. This is the resistance when the appliance consumes maximum power, that is 840. Now, we want to find out current and resistance when the appliance consumes minimum power. When the appliance consumes minimum power. See, again, for minimum power, we want to find out current and resistance. I is equal to P by V. Here P is 360 by V. V is 220. So we can cancel 1 0 from up and down. Then again we can cancel with the 2. That means here 1 and 8. Here how much? 11. Now 18 by 11. 1 times 11, 7, putting 0. That is equal to how many times? 11 in 76 times. That means here it will come 6 times 11 is 66. Balance 4. Again 1 more 0. 40. How many? 3 times. So its value is how much? When the power is minimum. When the power is minimum, current I is equal to how much? It will be 1.63 ampere. It is the current. 1.63 ampere is the current. Now we want to find out the resistance in this case. See, current is 1.63, and to find the resistance we can use the relation. Which is the relation to find the resistance in this case? R is equal to V by I. That is equal to V here 220 itself divided by I. I is actually 18 by 11. See, 18 by 11 or 1.63. It is better we can use this 18 by 11. That is 18 by 11. This 11 come up. Then how much it will be? We can cancel with the 2. Here 9. Here 1, 1, 0. 11 times 11, 121. Then put the 0, that divide by 9. Now we can divide. That means 1, 2, 1, 0 divided by 9. 1 times 9, balance 3, 31. How many times? 3 times 9, 27. Balance 4 and 0, 14. How many times 9? 4 times. That means 4 times 9, 36. 4. Again 4. So its answer is 134.4 ohm. See, its answer is 134.4 ohm is the current. Current is 1.63 and the resistance is how much it will be? 134.4 ohm is the resistance when the power is minimum. So we got answer for current and resistance when the power is maximum 840 and minimum 360. Now we can go to the for see the next question. 100 joule of heat is produced each second in 4 ohm resistance. Find the potential difference across the resistor. That means 100 joule heat is produced in each second. That means in each second. That means in 1 second. That means the heat produced is 100 joule. In a 4 ohm resistor, 4 ohm resistor, find the potential difference across the resistor. Find the potential difference across the resistor. See, we know here time, that means power is given. That means or heat produced is given. Heat produced, that means H is equal to 100 joule. Time is equal to 1 second. R is equal to 4 ohm. H is given as 100 joule. T is equal to 1 second. R is equal to this, how much? 4 ohm. We want to find out the potential difference. We know the relation H is equal to V square T by R. From this we got the relation V square is equal to H into R by T. See here, H is how much? It is 100 into R, that is 4 by time 1. This is the value of V square. V square is equal to 100 into 4 by 1. 100 into 4 is 400. By 1 is 400 itself. So V square is equal to 400. From this V is equal to root of 400, that is equal to 20 volt. This is the potential difference. So the value of potential difference, here it is how much? It is 20 volt. Potential difference is 20 volt. That we want find the potential difference across the resistor. So potential difference across the resistor, we got this, or by using another relation also we can find out this one. That means from H is equal to I square RT. At first we find I, then we can get this relation. Okay. See, these are the two problems solved in our text. Now I hope you got idea about how to solve these problems. Now see, some more questions here given. Among that, first one is why does the cord of an electric heater not glow when the heating element does? Suppose we know in an electric heater, this is the heating element. This part is the cord. This heating element become red hot when there is electric current through it. But the cord, that is not get heated up. What is the reason for this happening? See, when electric current passes through this cord, current through this heating element and this cord will remain the same. That means current through these two are the same. But you see, the resistance of this heating element is very high. Resistance of this heating element is high. Because of that, this become red hot, or it will glow with heat like that of a fire. That means it become red hot. But when we comparing with this heating coil to the cord, its resistance is very small, so it is not get heated up. It is not get heated up because its resistance is very small or negligible. But here the resistance is high, so it become very high temperature due to heat. Now another one, compute the heat generated while transferring 96,000 coulomb of charge in 1 hour through a potential difference of 50 volt. See the question here given. Compute the heat generated while transferring 96,000 coulomb of charge. That means here charge is given. Q is equal to 96,000. This much coulomb. Then the potential difference, that means this charge flows through the conductor in a time of 1 hour. That means T is equal to 1 hour. And the potential difference applied, V is equal to 50 volt. Potential difference applied there is 50 volt. We know what is H is equal to the relation to calculate heat. H is equal to V I T. Here I is equal to Q by T. Here Q is 96,000 and T is 1 hour. 1 hour means 60 minutes, and this minute we can change to second. So I is equal to 96,000 by 60 into 60. And when we substitute the given values in this relation, H equal to V, at first V is here given as 50 volt into I. This I is how much? 96,000 divided by 60 into 60. And again time we want to take in second. So this time is here given as 1 hour. 1 hour is equal to 60 minutes. That is equal to into 60 second. So 60 into 60. Now we can cancel these terms. Now see, h is equal to 96 into 5. Then we can put the zeros. 96 into 5. 5 times 6 30. Balance 3. Then 5 times 9 40. 5 plus this 3. That is 48. So this will come as 48 without 0. Then remaining here 1, 2, 3, 4 zeros. This we can write as in terms of 4.8. Then how many decimal we put? 1, 2, 3, 4, 5, 6. Here we are putting decimal point. So this becomes 4.8 into 10 raised to 6 joule. How much it will be? 4.8 into 10 raised to 6 joule is the amount of heat produced within this time of 1 hour. Now another question here given is an electric iron of resistance 20 ohm. That means an electric iron of resistance 20 ohm takes a current of 5 ampere. Calculate the heat developed in 30 seconds. See here given resistance, current and time. So which of the relations we can use to calculate heat produced in this case? Can we use H is equal to VIT or H is equal to I square RT or H is equal to V square T by R or H is equal to P into T? Among these, which of the relation is most suitable here to calculate heat producing? See, R is given, I is given, T also given. Any relation we can use from this, but it is easy to use this relation among these four to calculate heat. So H is equal to I, that is pi square, into R 20 into T 30. We know pi square is 5 into 5 25 and 2 into 3 is 6. This. Now 6 times 25 is 150 and put 2 more zeros. That means heat developed is 15,000 joule. Here the heat developed is how much? 15,000 joule is the heat produced in this case. Okay? How to calculate this one? H is equal to relation which we here chosen. H is equal to I square RT. You can use this one, any of this relation. But here easy one is this H is equal to I square RT, and in this relation when we put the values, 5 square means 5 times 5 25, 2 into 3 6 and 2 zeros, and 25 times 6 is 150, then these 2 zeros, that is 15,000 joule is the heat produced in this case. Okay. Now we are going to discuss about the applications of heating effect of electric current. Applications of heating effect of heating effect of the electric current. Heating effect of the electric current. What are the applications or where we use the heating effect of electric current? See, when we discuss about the heating effect, we know what is heat is produced in all cases whenever there is a current passes through any device. A small amount of heat is producing. But in most of the cases, that heat producing is undesirable, or that is not necessary, but we cannot avoid that. For example, when we charge mobile phone, if we touch the charger, you can see that one is getting heated up or its temperature is increasing. Or when we use mobile phone continuously, especially when we use internet, then it's getting heated up. There also heat is producing. Is it necessary for us? It is actually not needed, but we cannot avoid that heating. So in most of the cases, heat produced by electric current is not desirable, but in some of the cases it is very much necessary, and there we use the effects of heating. See, in some of the appliances we use heating effect on where we use that means laundry iron, that means to iron our clothes. We use this heating effect. Second one in soldering iron. We use heating effect of electric current. Then electric kettle. We use heating effect of electric current. Then electric heater. We make use of the heating effect of electric current. Then in toaster, we make use of heating effect of electric current. Here you see, in these all cases, we use the advantages of heating effect of electric current in laundry iron, soldering iron, electric kettle, electric heater, toaster, immersion heater. In this all appliances, we make use of the heating effect of electric current. In some of the lighting devices, there also we make use of heating effect. For example, in electric bulb, we use the heating effect of electric current. In an electric bulb, there is a filament. It is made with a metal tungsten. In electric bulb, there is a filament and it is made with a metal tungsten. See, its melting point is very high. That means above 3000 degrees Celsius. That means 3380 degrees Celsius is the melting point of this tungsten. That means it will melt only at this temperature. That means when electric current passes through this tungsten filament, it becomes white hot. It becomes white hot condition, and it can remain in that condition for very long time. So the electric energy given there is converted into heat. From there, a small part of electric energy we get as light. Nearly 60% of electrical energy supplied there becomes heat. Somewhat 40% of energy only we get as light. See, in electric bulb also we make use of what is a heating effect of electric current. In electric bulb there is a filament and it is made with what is a tungsten, and its melting point is 3380 degree Celsius. At that temperature it can emit light, and most of the energy here utilized as heat, and a small part of energy we get as light. And in this electric bulb we fill gases such as nitrogen or argon to extend the lifespan of the filament. That means nitrogen can reduce nitrogen and this argon. Argon is an inert gas. Nitrogen is also behaves like an inert gas at low temperature, and these gases reduces oxidation and also evaporation in the bulb. That means especially the filament of the bulb. So its lifespan can be increased. Lifespan we can increase by filling it with what is which gas we are using there? Nitrogen and argon. What is the advantage of this gas? It reduces the oxidation of the filament. It reduces the oxidation of the filament. So in electric bulb also we use what is a heating effect. Then another device, that means electric fuse. In electric fuse also we make use of heating effect. In electric fuse, what is the purpose of using fuse in an electric circuit? Fuse in an electric circuit that protect the circuit and the gadgets or appliances that are using in the circuit from the dangers of overcurrent. Dangers of overcurrent. That means electric fuse is a protective device. It also works based on heating effect of electric current. That means electric fuse, how we connected in a circuit means it is connected in series. It is connected in series in the circuit. What is the use of this one means it is the purpose to protect electric circuit from the flow of overcurrent. How the fuse protect the circuit means this fuse is connected in series. That means all the current that flows through the fuse wire, in all time there produces a small amount of current, but the amount of heat produced that transferred to the or dissipated to the surroundings. So there is not producing excess heat. But when there is the current is very high, what will happen? The heat produced in the fuse wire becomes very large, and that does not transmit to the surrounding at the same rate. So the temperature of the fuse wire will increase and it melts. Normally we use fuse wire by using aluminum, copper, iron, lead and tin. In our household circuit, we make use of an alloy called lead and tin wire as fuse wire. Its melting point is low, so whenever the temperature increases tremendously, what happens? It melts and breaks the circuit, so it protects the circuit. Now see, here electric bulb, there we use heating effect in electric fuse or safety fuse. There we use heating effect of electric current. Now see how the fuse is connecting. That means that is connected in the circuit. How in series we know what is a fuse wire is fixed in a porcelain carrier. Fuse wire is fixed in a porcelain carrier, and the fuse wire edges comes out to connect it to the circuit. This porcelain carrier is an insulator, so we can handle it without getting electric shock. Now, for example, an electric kind of power 1000 watt in a 220 volt supply. Then the current through it is that means I is equal to current through it I is equal to P by V, that is 1000 divided by 220, that is equal to, again we can cancel 11 and 50. 50 divided by 11 times 4, 44. Balance 6, 60, 5. That means current through that electric iron is 4.5 ampere. So there we use a fuse wire of 5 ampere. That means when we use an electric iron of power 1000 watt under a potential of 220, then the current through it is how much I is equal to P by V. By simplifying we will get it is 4.5 ampere. So the fuse wire there we use is how much it is 5 ampere. We use a fuse wire of 5 ampere there. Okay. In our household circuit we will get a fuse wire such as 1 ampere fuse, 2 ampere fuse, 3 ampere fuse wire and 5 ampere, 10 ampere. These are the fuse available in the market to use in our household circuit. That means always we want use fuse wire in accordance with the power we using in our household circuit. That means if we use very small amount of current, then no need to use fuse wire of very large. So we should take care of the fuse wire and the current or the load which we using in our circuit. Now these are the applications of heating effect of electric current, where we use it we used in laundry iron, toaster, electric kettle, then electric iron, then electric heater, etc. Then also we use where it we used in electric bulb and also in safety fuse or electric fuse. Now one more things we want to remember from this unit is the power. What is actually power? That is the rate of doing work or rate of consuming electrical energy. Rate of doing work or rate of consuming electrical energy. See, what is actually power? It is the rate of doing work or rate of consuming electrical energy. Here, see the relations we know H is equal to I square RT and also H is equal to VIT. H is equal to V square T by R. Here all work done or energy used in time T. When we consider rate of doing work, see P is equal to actually H by T, rate of doing work. So from these relations, P is equal to H by T is equal to I square RT by T. So it will get us I square R. This is the power. And from these relations, P is equal to H by T is equal to VIT by T. So it will get VI. And from this relation, H is equal to V square T by R by T. So we get it as V square by R. These are the relations we can use to calculate power in an electric circuit. Power in an electric circuit is equal to how much? P is equal to H by T, that is equal to I square R. P is equal to VI and P is equal to V square by R. These are the relations that we can use. You want to remember which unit is using to calculate electric power. The unit of electric power is watt, and its symbol is W. That means power. The unit of power is watt. Now see, power, it means power P is equal to, we know, for example, VI, or from this voltage by current, that is equal to what? These relations. Now power is 1 watt means, suppose power is 1 watt. If 1 ampere current flows through a circuit under a potential difference of 1 volt. If the current through a circuit is 1 ampere under a potential difference of 1 volt, then see power P is equal to 1 volt by 1 ampere, that is equal to 1 watt. That means if a current of 1 ampere flows to a circuit under a potential difference of 1 volt, then power is 1 watt. Power is how much? 1 watt. Then you want to remember about power. This power watt is very small, so we use what is watt hour is using. Watt hour means this 1 into power, that is 60 into 60. That means 3600 watt. And in electric energy supplying device for commercial unit of electric energy is actually commercial unit of electrical energy is commercial unit of electrical energy is that means kilowatt hour. Kilowatt hour is the commercial unit of electrical energy. Kilowatt hour means that means 1 kilowatt means 1000 into watt hour means 60 into 60, that is equal to how much? 6 into 6 36. How many zeros on 2? Then so that is equal to 3.6 into 10 to the power 6 joule. That means kilowatt hour is actually how much it will be? 3.6 into 10 to the power 6 joule is the kilowatt hour. See, electrical energy when we calculated, that means electric power which we supplying in which unit? Kilowatt hour, which is the commercial unit, and 1 kilowatt hour is equal to how much? 1 kilowatt hour is equal to 1 kilowatt means 1000 into hour means 60 into 60, and that will get us 3.6 into 10 raised to 6 joule is the kilowatt hour. See, we discussed about what is actually heating effect of electric current and its applications, where we use heating effect of electric current, and then what is actually electric power and the relations which we can use to find electric power. With this all, we can conclude our class today. Okay, thank you.